Watch this phrase, a loyal pet, become a single point in space. It lands right next to dog and puppy. That's meaning turned into geometry. Welcome to AI Tech Book. Today, embeddings and vector search, how a machine turns meaning into points in space and finds the closest one out of millions. Start here. An embedding is how a model turns meaning into a place. Every word, every sentence becomes a point in a space with hundreds of dimensions. And the space has one beautiful rule. The model places things so that similar meaning sits close together. Dog and puppy land in the same neighborhood. Pizza and sushi in another. Python and function somewhere else entirely. Guitar and piano their own corner. You're not looking at a word cloud. You're looking at meaning arranged as geometry, where distance is similarity. So if meaning is a location, then what's related to this? Becomes a much simpler question, what's nearby? But a point in space is really just numbers. What are they? Underneath the point is a vector, a fixed length list of floating point numbers. Here's the thing that makes it work. Every input, short or long, becomes the same length, often a few hundred to a few thousand numbers. Around 1,000 is typical. Each number is one coordinate of the point. One practical note, Claude itself doesn't hand you these vectors. You use a dedicated embedding model. Anthropic recommends Voyage. The language model generates, the embedding model vectorizes. And because every embedding is the same length, any two of them are directly comparable number by number. Comparable how? What makes two of these close? Here's the part that surprises people. You don't measure closeness by length. You measure it by the angle between two vectors. It's called cosine similarity, the cosine of the angle between them. Point the same direction, and it's 1. Perpendicular, and it's 0. Opposite, -1. Watch. Dog and puppy start apart, then swing together until they almost overlap. And the score climbs toward 1. Piano stays off on its own, near 0. It cares about direction, not length. And a neat fact, once the vectors are normalized, ranking by angle and ranking by straight line distance give the exact same order. So to find related things, you look for the smallest angle, which means you can search by meaning. Now the payoff. Take your question, embed it with the same model, and you get a point. Drop it into the space, and look at what's nearest. Watch the query, a loyal pet lands near the animals. The rest of the space falls away, and its nearest concepts light up, dog, puppy, cat. That's vector search. You find the points with the smallest angle to your query, its nearest neighbors, and those are your results, ranked by meaning. No keywords. No exact match. A loyal pet finds dog and puppy because that's where it landed. This is semantic search, and it's the retrieval half of RAG. But a real corpus has millions of points. You can't check every one, or can you? Here's the honest catch. Finding the true nearest point means comparing your query against every single vector. That's order n fine for thousands. Far too slow for millions on every search. So you switch to approximate-nearest-neighbor. The popular approach builds a navigable graph. The search enters at the top and hops along a few edges, straight to the right neighborhood. Logarithmic, not linear. You trade a tiny bit of accuracy for an enormous speedup. And this all lives inside a vector database, pgvector, face, pinecone, weaviate. That's what makes meaning search work at production scale. And the single biggest thing it powers. Retrieval augmented generation. Embeddings are the engine underneath it. Here's the whole loop. Offline, take your documents, split them into chunks, embed each chunk, and store the vectors in a vector database. Then, at question time, embed the query, retrieve the top k nearest chunks, and feed those chunks to the model as context. The model answers from text it just retrieved, grounded, current, and yours. Embeddings are the retrieval, the model is the generation. And the better your chunks, the better the retrieval. What you embed is what you can find. So where does this geometry quietly lie to you? 4 traps, each a place where the geometry stops meaning what you think. 1. Vectors are model specific. A vector from one model is gibberish to another, so embed your corpus and your queries with the same model. 2. The famous word math, king minus man plus woman equals queen. That was a cherry-picked trick of old word vectors. Don't expect clean arithmetic from modern sentence embeddings. 3. Semantic search misses exact strings, a product code, an error ID, a name. So blend and keyword search, that's hybrid. 4. What you embed is what you can retrieve. Embed a 50-page document as one vector and it blurs every topic into mush. Size your chunks to one idea. Respect those 4 and the geometry stays honest. So, the whole thing in one line. Embeddings and vector search in one breath. An embedding turns meaning into a point, a fixed length vector. Closeness is the angle between 2 points, Cosine similarity. Search is embedding your query and finding the nearest points, semantic search, the retrieval in RAG. And at scale, an approximate nearest neighbor index inside a vector database makes it fast, meaning turned into geometry. That's the quiet engine under modern search. The whole thing, one screen. Meaning becomes a point, a vector. Closeness is the angle between them, cosine. Search is embedding your query and finding its nearest points. At scale, an approximate index in a vector database keeps it fast. And the traps, one model for everything, and add keyword search when exact strings matter. Meaning becomes a point, and similar meaning lands nearby. That's embeddings and vector search, meaning as geometry. If this made the idea click, share it with one person building search or RAG. Subscribe to AI Tech Book, one architecture concept every episode. Thanks for building with us.